So we
All
have
right.
Sergio Ferragut here. I'm going to turn it over and let him share. And as usual, Ike and I might chime in a little bit with questions, and you are welcome to throw questions in chat or unmute when we speak. So, all right, Sergio, it's all you.
Thank you. And thanks for using my real name. So I'm Sergio Ferragut, as Dustin said correctly. People call me Sergio because, I live in the States. I work for Imply. I am a senior developer advocate for the Apache Druid project. And we're here to talk about the rise of immediate intelligence. So this is about the history of the Apache Druid database, the history of analytics and cold versus hot analytics. And I'm talking to the next slide now. So we're talking about the data temperature. We're going to talk about the history, how databases evolved and got to this, Druid's own story. And then we'll dig in a little bit, looking under the hood and understand a little bit about how it works, how it delivers the speed it does. And I'll leave you with a few more learning tools if you want to learn more. All right, so let's talk about data temperature. So we're trying to create a contrast here between hot analytics and cold analytics, right? The traditional world of BI is where we're placing cold analytics, right? Where it's a data warehouse, it's the data lake that where nobody likes a slow query, but slow queries are actually okay. I mean, it could take a few seconds, even a few minutes. You can go get your coffee while the report's being created, and it's okay. The analytics space is okay with that kind of performance, right? Typically, the data is not real time data. It's daily batch data is what you typically get in these kinds of environments. So the data isn't it's not completely fresh. It's fresh-ish. Um, Typically there's low concurrency in these environments, right? You're talking about probably at the high end, you're talking about a few hundred users, not thousands or millions of users. So that's what we're calling low concurrency. And again, this is about reporting. It's about strategic decision making, not necessarily the real time decision making. So in contrast, the hot analytics are really about fast queries, right? This is most of the time we're talking sub-second response times. We're trying to drive analytic applications that require that users are interacting with, and users will not wait around for 5 or 10 seconds for the next click, right? So it's that kind of speed. It's a end user, high concurrency, up to millions of users, and providing a very highly interactive experience. And I'll show you a little bit what we mean about that. And one of the more important things is the fresh data, right? And what we mean by fresh data is streaming data, and not just the streaming data, but streaming data along with historical data, so you can create time comparisons and understand what's happening now in the context of what's happened in the past. So I touched on a few of these, so I won't spend too much time on this slide. But so immediate intelligence is focused on the day-to-day decisions, right? On multiple decisions a day, instead of the strategic focus of business intelligence. The audience is meant to be everyone. So these are end user applications. These are analytics embedded in mobile apps, in websites that need to provide fast analytics. Um, so the knowledge is more operational. It's about doing your job, right? Whoever the person is that's using these analytics, it's about doing their job and having the analytics readily available to do their job. So it's instinctive, it's ad hoc, instead of comparing to business intelligence, comparing to more methodical research and reflective. Um, and it's intended to be a catalyst for business decision driven adaptation. So moving things faster, right? Empowering the all of the business users, or even like the consumers or the customers, to use the analytics with the most recent data. So a few use cases to try to nail this down a little bit more. In risk and fraud space, right? We see in finance, you have millions of transactions. Let's take credit cards, for example, right? Millions of transactions that are occurring really quickly, and and it's a lot of data. If you're streaming that and you want to be able to compare that to profiles, right? To what the behavior has been over the recent time and over the history of that each user's profile, in order to quickly make a decision about whether a specific transaction may be fraudulent. Data-driven applications. These are, websites with typically have lots of users. So we're talking about very high concurrency and fast-moving data. Network performance is about looking at individual packets and their transition through network devices, understanding, aggregating to understand traffic in different parts of the network, and recognizing security events or just failures in infrastructure, and therefore being able to provide a consistent and reliable network behavior. Clickstream is all about understanding, one click and what they clicked on first, what they clicked on next, and so understanding the journey of each user within some interaction, within some application, and then being able to analyze that data to understand what the patterns of different journeys are. And in the extreme case, it's about looking at what users' sessions are doing right now. So in real time, looking at what users' sessions are doing and comparing those to other user sessions, and being able to shape the journey for a particular user based on what they're doing and based on what you know about them. So it's this, in general, you have to think about it as this combination of really fast analytics that allow you to create, and I'll show you an example of that in a second, but to be able to have a conversation with the data at this and that on historical data and also on real-time data, to be able to create these reactions to interact to customer interactions, to IoT devices, to things that are occurring now. I won't go into all of these because the deck is rather large, but I will touch on digital ads a little bit more, because that's where Druid was born, and so I'll talk about the history of Druid in a moment. So let's talk about in general the evolution of analytics in the database space, right? So we go back to when I started building applications back in the 90s. We were building applications on relational databases, right? These are transactional systems. We were trying to automate the operation of businesses, and in automating business processes, we were gathering data, right? We were starting to create a database of transactions, of interactions, and obviously the business analysts wanted to have access to that, right? And wanted to be able to create reports on that. So we started creating these applications, and suddenly we started putting a bunch of reports on the same database, or a bunch of queries on the same database, that weren't necessarily transactional. They were spanning large amounts of the data, and we started seeing contention between the transactional workload and the analytic workload. So the first thing that happened, and instances of this, that everybody knows, Informix, Oracle, SQL Server, we were building applications in all of these databases and others. But when this happened, then so the architects at the time decided, well, we need to separate these workloads, right? So let's take the analytic workload out of the transactional systems, and we started doing the separation of OLTP and OLAP, online transaction processing and online analytic processing. And in doing so, examples of these are Teradata, Oracle, Netezza. These data warehouses, these were platforms that were scalable. They weren't cheap to scale, but they were scalable. And along with this came this process of ETL, right? This is the idea of, let's extract on a periodic basis the data from the transactional systems, bring it into the data warehouse, and allow users to do their analytics and reporting, and build reporting tools on top of the data warehouse, so that all the work is there, and we're no longer bugging the operation. We're no longer at risk of stopping the operation because we're running a bad query, right? So by separating the workloads. So this worked, although this also, I worked in data warehouse. I used to work at Teradata in professional service, so I did this for a living. And building data warehouses was not easy, right? It was there was a long process of analysis of source systems, analysis of the business, modeling the business in third normal form. That was the Teradata way, and moving all of the data from all of these source systems, transforming it, cleaning it, and putting it into the data warehouse. And that took time. So if we think about the hot and cold analytics analogy, we this became cold, and it became cold because when a business user wanted to do something, they probably, if they were lucky, some of the data was already in the data warehouse, and then it was just about building some new dashboard or some new report. But if they were unlucky, then it was about 3 months worth of analyzing source systems, extracts, transforms, and loading the data to get to their results. By the time they got the results, that in many cases they weren't interested anymore. So that was a cold experience. Something that made it hotter, right, was the appearance of data marts. So we started separating this Uber project that was the data warehouse into smaller star schemas, or we started implementing user interfaces like Click and Cognos that allowed the business user to come to the tool and build the reports on their own. And this helped, right, because they could now solve the problems on their own, as long as the data mart that they were building was specialized for the data that they wanted. These data marts were aggregated subsets of a data warehouse, and they were usually focused on a specific business area: sales, marketing, the inventory, the supply chain, etc. So this helped. It definitely made things hotter. They became very successful, and we saw the appearance of data marts all over the place. Even those rogue data marts that wouldn't go through the data warehouse because they didn't want to spend the extra 3 months to get the data they needed, and they went directly to the source systems, which IT always loved. So that was the stage probably around the beginning of the 2000s or something, right? At that point, or a few years later, 2000 something, we started seeing big data appear. We started seeing it in multiple forms. We started seeing it on the OLTP side because the transaction volume started growing, and the single instance, a single server, could only scale up so much. So we started seeing this concept of distributed computing, right? And OLTP databases that were sharded in order to be able to do larger amounts of transactions concurrently by distributing the workload across multiple instances of the database. And we saw things like Mongo, Cassandra, and Couchbase appear in this space. And the rest of it seemed similar until things changed again, and the data lake appeared. Now, the data lake is a slightly different idea, right? The data lake is this idea that the data warehouse and this whole ETL process is it takes long. So what if we don't do it, right? What if we just take the source systems, extract the data as is, and put it all organized into a data lake, and then make all of this data available to those who want to query it. In order to achieve that, along came a bunch of distributed query engines. So this analytics side also scaled out by creating using the distributed compute patterns to access the data lake and process things in parallel and build out analytics at scale. Now, one thing that we like to point out here is that the ETL actually didn't disappear, right? The ETL still there. It's now on the query side, though, right? The users who are building these analytics or building these reports or implementing these query engines need to still understand the sources, need to understand what's in the data lake. Otherwise, many have said this, the data lake becomes a data swamp unless somebody can make sense of it, right? So we saw things like Kylan, Hive, and Trino appear in this space, in the space of distributed query engines. Now, this helped, right? This gave a lot of end users the ability to innovate with whatever data they wanted because the data was there, and so we see the appearance of machine learning again because of the availability of the data, and not just machine learning, a bunch of different analytic capabilities with these kinds of new distributed query engines. Now, problem with this is still it's not delivering that fast experience that I've been talking about, right? The sub-second response time. These query engines have to go and read, files from something that's probably not even local, right? It's in the cloud, and that takes time. It takes time to bring in the data and process the data. You could co-locate it in the cloud, but still, there's significant latency, or significant enough latency in gathering the data, transforming it, and then processing it to produce a query, such that it's not sub-second response times. We're talking, multiple seconds in the best case scenario, right? So we saw, well, and to make matters worse, right? It wasn't just the transactional systems that were managing the operational system, the operations of the business. We started seeing many more sources of data, right? The log data from websites, IoT devices. We saw the appearance of streaming engines like Kinesis and Kafka, and distributed processing engines like Spark. To process the data in real time. But a lot of what was happening is we were consuming this data that was coming in real time and putting it in a data lake, right? And then querying the engine. So the data that was readily available wasn't necessarily usable immediately in this platform. So this is where this concept of a serving database comes in. The idea of a serving database was to accelerate, to serve applications, right? To serve applications and provide that fast response time. So the intent here was let's take a subset of the data lake that we're interested in, transform it in some way so that we leave the data in the serving database in an optimized form for fast querying, right? And a lot of implementations, or the initial implementations of this model, were done on things like HBase, HBase and other key value stores that that had the advantage of, if you have a key, you can get the value really fast, and you can do that at scale. But in order to create the analytics had to be pretty static, right? That means that we had to build analytics ahead of time in order to attach them to a given key, and therefore it wasn't very ad hoc. While it did serve the purpose of scale and serve the purpose of fast response times, it wasn't very versatile. It wasn't very adaptable to user needs, and therefore still had that problem of being able to address new user needs quickly. So this is where Druid appears, and I'll go a little bit more into Druid's specific story. But Druid is a serving database, right? It's different than a key value store. Because it's not a key value store. It's actually a columnar store, but it has its own format for the data, and we'll go into what the data format is like and why that makes it fast. But it is an optimized copy of the data, of a subset of data, and it's meant to serve applications. It's meant to serve this interactive experience for applications. It also has the advantage of being able to directly hook up to streams. So you can load data in batch, and you can load data in streams, and you can query both of them concurrently, such that you can see the now and the history, and create queries that are useful from that perspective, and with the same fast response times. So let's go a little bit into Druid's specific story. So Druid started, like I said, in the ad tech space, right? This space of publishers that have ad spaces available, and where advertisers, and it's a very competitive space, right? The advertisers are looking for the best spot for their ads, and being able to analyze how well the segmentation that they're using is working, and how their ads are responding, what the click-through rates are. It's in this space that Druid was born, in a company called Meta Markets, where what they were trying to do is provide a new experience for these users where they could, in real time and with a really fast analytic capability, provide OLAP functionality, slicing and dicing, drilling across, drilling through, across different moments in time, all with sub-second response times. And they tried everything, right? Well, this is what that looks like, right? So this is an example of this the interactivity that they were shooting for, right? This is what I'm showing you here is actually a product of the company I work for, Imply. So this is Imply Pivot, which is a visualization tool that's optimized to query Druid, to query Apache Druid. But it's the database that's providing these response times, right? These videos are not accelerated. These videos are actually in real time. And you can see the interaction, as you pull in new dimensions to drill into the data in different ways, that it's responding with sub-second response time, and that was what they were looking to build. So they tried everything. They tried, the whole history that we just went through of databases. They tried it all. They tried relational databases. They tried a lake. They tried the warehouses. They tried search engines, time series databases, and in every single case, they found issues that were limiting the vision in order to create that interactive experience. They couldn't build it. So, and the problems were, in some cases, it was unscalable or prohibitively expensive to scale. The data was disjointed. The now event data was separated from the batch data, and it had to be queried separately. And this was limiting, and it was too slow for the experience that they wanted to deliver. So instead of using an existing technology, this group of engineers decided to build a new database, and that's how they built Druid. And they started with these requirements, right? It had to be high performance. It had to be low latency, a distributed query execution to deal with large amounts of data. It had to be in real time, so it had to be able to take in event data, streaming data, and be able to provide analytics on that data, things like counting, ranking, and statistics. And it had to be a database, right? It had to be highly available. It had to be time charted because they were, keeping history of events. And one of the principles was to divide the time up into chunks so that it could be the analytics could be parallelized for the different time chunks. They built it. Well, let's go into a little bit more of how they decided to build the data structures that delivered on this. So they learned from their experience of looking at other databases, right? From search engines, they took the ideas of real-time ingest, so this fast capability of ingestion, a flexible schema. From time series databases, this low latency ingest. So that's the from the moment an event occurs to the moment an event is actually queryable. That's the latency that we're looking for, and make that really short. And it used they took the idea of time-based storage and time functions to separate the data out into time chunks, and the ideas of columnar databases, right? Where because columnar databases have more efficient storage and have been proven to be faster at analytic queries, and the idea of data distribution that columnar databases use. So they took all of these ideas and built a new database out of it, and it works, right? It's a database that in the largest instance that I know of at this point is a 5,000 node instance. That's Twitter's. They actually have a public video on that if you want to look for that. So it's extremely scalable. Right, it's been proven to process more than 1 million events a second, streaming. And while providing this really fast response times and this interactive experience that you saw in those example applications. This is what their original application looked like. They built it. They were successful at it. But as they were building this database, they decided that from the very beginning that they would do it open source. So the Druid has been open source from the beginning. It became an Apache project, I believe, I'm going to miss the date there. I don't have my notes, but it was 2013, I believe. And as soon as it was open sourced, one of the first adopters was Netflix. which was interesting because it's another big data company, right? Another internet company, high tech, that they were running into the same kind of problem, right? They needed to be able to address real-time events while understanding the history of that data, and do it quickly, and being able to process ad hoc queries on that data. And they hadn't found any other technology to do it. So they started using Druid, and they started contributing to Druid as part of the open source project. Soon came many others, and this group here became the initial PMC, so the project management council for the Apache Druid project. And soon came many more, right? There's hundreds of implementations. I think there's over 1,000 implementations of Apache Druid out there in the wild, and that are taking advantage of this high performance, fast analytic capability. So how does it do it? You have a question, Dustin. You're muted.
There it is. I double clicked. I just wanted to jump in and just say, if there's anyone that does have questions as he's about to get in deeper to how it works, probably now's a good time to throw some in chat. The history you showed, the the story you told was really good. I appreciate kind of how quickly you're able to go through the history of that. I think as we get into it, the question I'm still kind of wondering, just to prompt you as you go, is, so what if I'm putting in log data or clickstream data, like how much history am I keeping, and what happens with things like updates? Is it kind of append only in some of those sorts of things?
So it does create immutable files, and we'll go into what the files look like in a moment. But to answer your question directly, is that I haven't seen a limit, right? So how much history do you want? How much do you need, right? And because it's a very scalable platform, you can deploy it in such a way that fits your needs, right? We try to make sure that people understand, and that's why we show that history and where it fits in the data landscape. This is not a data warehouse, right? And it's not meant to be a data warehouse. This is a database that's meant to drive applications, right? To drive interactive applications, to drive really fast response times. So whenever you're thinking of such an application, you don't want to bring all the data in like a data warehouse, right? You want to bring the data in that you need for that purpose, and you can do, it's scalable, so you can bring in as many different tables or as many different use cases that you want. It's just not designed to be like a data warehouse where you're querying everything against everything. You're querying specific things to deliver on specific functionality very quickly, right? That's sort of its goal. That interactive experience, whether it's on historic data or real-time data, you can do both. That help?
So this would fall into the category of a NoSQL database, right?
It's I guess, but it is SQL.
Yeah.
It's not a relational database. That's really what I think we're trying to say here, right? When we say NoSQL, it is. I'm not going to get into the details of the execution model, but today it's a scatter gather execution model, which means that there's I'm actually going to go into the architecture, and I'll talk through it just in that slide. Let's
cool. I'll let you keep going here.
Yeah. Thank you. If I forget any of what you just asked, make sure to let me know. So anyway, I'm placing it here again, just to again set the landscape, right? This is the data landscape, the overall data landscape, and this is where Druid fits. So this is the Druid architecture, right? It's a highly scalable architecture, so you can have many master servers, many query servers, many data servers. But just to follow the logic here. There are three main things going on in an Apache Druid database. One of them is data ingestion. So on the right, we see the streaming data or batch data. It's the indexer processes that run in the data servers that do this, and they're highly scalable as well, right? So you can scale out your indexer processes in order to deal with more streaming bandwidth or larger batches, and still keep the time short. One limitation on the streaming side is it's going to be as parallel as the number of partitions you have in Kafka, or the number of, I believe they're called shards in Kinesis. So that becomes your limitation. Your whole pipe needs to be as wide as you need it in order to deal with the throughput that you're looking for. But the point on the Druid side is that we haven't seen a limit to its scalability, right? You can create more and more indexers in order to drive more ingestion capability. The other thing that's going on is, so as the data is ingested, they produce these segment files. We've mentioned that there's producing immutable files, which are called data segments. These are files that contain approximately, it's not an exact number, but the recommendation is around 5 million rows in each one. It stores it in a columnar structure, and we'll get into the details of the structure in a moment. But so the indexers take the data in, they keep it in memory. If it's streaming, they keep it in memory, and we'll touch on that in a second because it's for query purposes. They keep it in memory while they're ingesting it. They produce this columnar structure and produce this immutable file that they push to something called deep storage. So that's at the bottom of this diagram. Deep storage can be things like S3, Azure Blob Storage, any cloud storage or distributed file system like HDFS to permanently store this data, right? To persist and to guarantee that that data will be there. Then there's another process that takes those segments and distributes them and distributes replicas across the historicals. So historicals are these other processes in the data servers that serve queries, and they serve the historical part of the query. So the coordinator process recognizes all of the data segments that have been loaded and distributes them across historicals for parallelism, distributes replicas across historicals for high availability. And so that's the data management process that's going on. And finally, the query process, right? So queries arrive through the query server or query servers, right? There could be many of them, through a microservice called the broker. The broker is also has all of the metadata related to which segments of data exist where, so which historicals contain which segments of data, and they also know which real-time segments are being loaded into the indexer, so what's in memory in the indexers. So when they receive a query, they look at the time frame for the query and distribute subtasks to the appropriate historicals, the ones that have the segments that they're interested in on the historical side, and they talk to the indexers for the real-time portion of the query. All of these return the queries, their portions of the query back to the broker, and the broker does the final, final aggregations if there's a final aggregation to be done, having clauses, that kind of thing, and then returns the results to the user. So before I move on, I know that's a lot, so I'll stop for questions here if there are any. All right. Well, let me see the chat real quick. Oh, yes, Druid does need Zookeeper. Sorry, I didn't mention Zookeeper specifically. Druid was designed originally with Zookeeper. Zookeeper is used as an inter-process communication mechanism. So for example, the coordinator is telling the historicals which segments to pick up. Right, it puts those instructions into Zookeeper. The historicals each read their instructions from Zookeeper. So it's a communication mechanism. It's also used for quorum to do leader elections. So the coordinator processes run usually 3 instances of them. There's one that's the leader, and in a case of failure, the process of selection is done through Zookeeper to select the failover leader for that. I believe that's all the functions that Zookeeper does. There are options of the inter-process communication without Zookeeper. One of the things Druid has is its architecture, its code architecture is actually quite interesting. It's built with a lot of extensibility, and so they've built out everything using good coding patterns, such that other parties can create extensions for any of the operations that make up Druid. So there's been a lot of contributions by other developers from other companies, enabling different capabilities of Druid because of this coding infrastructure. And one of those is using a direct HTTP communication between the coordinators and the other processes instead of Zookeeper. So there are two options there. But anyway, I'm digressing and getting into too many details there. So Dustin, you have a question?
Yeah, and so I think it's just going to make you repeat a bit of what you just
That's fine.
said a moment ago before the Zookeeper talk. So when I think of analytic databases and speeding them up, I usually think of caching in some way. And so
Mm-hmm.
I'm trying to get my head around with the deep storage versus historical. Is it similar to caching in other
It
systems,
is.
or is there stuff that's okay?
It
Go
is
ahead.
absolutely a cache, right? And there's
Okay.
actually two levels of cache there, right? So one of the things that's different from the other query engines we've talked about, right, is many query engines go to what we consider deep storage, so to S3, grab the data from there and process it, right? And like I said, there's some latency there, so bringing the historicals load the data locally. They always have the segments in their local storage, um, and you can configure historicals to use SSDs or hard drives, right? So the speed of access to that data locally can be different depending on your deployment. And you can actually deploy, and I'm getting into too much details, but you can deploy multiple tiers of historical. So you have a tier that's like a hot tier versus a cold tier, and have the data automatically migrate from one to the other as it ages. Um, so you can have different hardware associated to different sets of historicals based on the recency of the data. Did I answer your question there?
That was very enlightening. Yeah, I
Okay.
guess the follow up to really try and drive it home, at least for me, is all of the data in deep storage also available in historical when the cluster's running, or is some of it need retrieved when it's
So
asked for if it's not on there already?
it is all there's actually more than all of it. So deep storage has one copy of each segment, right?
Okay.
The historicals will have at least one historical will have a copy of each of the segments, and you can define the number of replicas that you want in order to provide high availability of the historicals, right? So you can have multiple copies of each segment distributed across historicals, which are not just dormant copies; they're actually active copies of the segment. They're used to query in parallel, query the same data in parallel, but they also provide high availability. And one more thing about caching is these historicals take they have the segments locally in their local storage, but they use memory mapping, the OS level memory mapping to bring the each of those segments into memory and use them. So you can configure historicals. The ratio of memory to storage can be such that it's very likely that the segments are already in memory when you're reading them, and that speeds up historical analysis quite a bit too. So there are many different deployment models here that can take more advantage of the caching, and obviously they're more expensive. The more memory you have, the more SSDs you have are more expensive, and that's why there's the tiering idea, so that you can have the very hot tier with tons of memory, very fast CPUs, lots of SSD, and that's where you do, I don't know, the most recent 2 weeks of data, and then from there you create another tier of historical that may use hard drives, less memory, so there's a lot less caching going on, um, and they're slower for 2, 3, 4 years of data that you may want to query on the historical, but you may have not as stringent SLAs on, right? So anyway, that's the model. You can decide how much you put on each one, how big you make each tier, and so forth. So let's get into the data. Well, any other questions around the architecture before I move into the data?
Looks like we're good right now, unless someone
All
wants to
right.
mute really, really
All right.
quick. Otherwise, throw them in chat and we'll get to it the next little
All
briefing.
right, let's go. So the data uses 4 different strategies to how the data is structured. The data is compressed. It's columnar. All dimension columns have secondary indexes automatically. We'll talk about the two kinds of indexes they use. They each create a dictionary. So this is a dictionary of the distinct values of the column, that of the values that appear in the column in a particular subset of data. And that dictionary is used for the encoding, that the data is actually encoded into these numbers, so you can see, and that allows for much better compression. And finally, uses late materialization, which is this idea of processing the data in its compressed form, and only towards the end of the operation, taking the values from the dictionary and rehydrating the data with the values to return to the user. So this keeps the memory footprint small and keeps things efficient. So this is an example of such a data structure, right? So the first column we see is time, and you'll always see time in the in a Druid table, right? You can have tables that don't make use of time, just have a constant value in the time column, but that's not the common use case. The common use case is we have event data, right? And events have time, so there will always be a time attached to each row, right? Then there will be dimension columns. In this case, we have artist and city. You can see that in the artist case, let's talk about that one. We have three values, right? And the dictionary. So the dictionary is created out of the distinct values within the data set, right? And here this is a small example, but usually there's 5 million rows per each of these files. So with the dictionary, we have the distinct values and they're sorted, so that makes them easily searchable. We associate an index to each one, and then what the index tells us is for each entry in the index corresponds to that entry in the dictionary. So what the index here is telling us is that ACDC appears in rows 0, 1, and 2. And right alongside that, there's a bit field, right? This is a bitmap index, and they're really interesting because it's a simple idea that I found quite powerful. So it's a bit per row, right? And you see the bits are turned on if that value is present in that row, right? So this tells us again that 111 is ACDC appears in the first 3 rows, and then it doesn't appear in the other rows. So this has multiple capabilities. One is it allows us to do multi-value columns. So you can have a column that might have ACDC and Kylie as a list of values. And in that case, you would have in the index, you would see that, right? That it appears in more than one row, and the bit field would have that turned on for those 2 values. This becomes incredibly interesting when you start combining where clauses. So if you're doing a combined where clause where artist is equal to ACDC and city is equal to, let's say, Perth, then you can take the bit fields of each of those entries and just and them or them or do any kind of bitwise operation on those bitmaps to resolve the where clause and find the rows that are relevant. So. And finally, you have columns that are metrics, right? These are the values that you're storing, and those aren't stored in any particular form, just in a separate column each one. So let's walk through an example using this data structure. So this is a simple query, right? We're looking for the total sales by city for a given artist, in this case for ACDC. So the first thing that happens with a query like this is we read the artist columns dictionary and we find the value, right? So like we said, it's a sorted list, and so it's very quick to find a value within the list, even if it's not the first one in the list. But we find that value, and with that value, we can go directly to the index, and that tells us which rows that appears in. Once we know which rows that appears in, that's 0, 1, and 2, we can then go to the other columns that we're interested in. We're interested in city and price. So we take the values from the rows 0, 1, and 2, from the city column and from the price column, and we do the operation, right? We do the aggregation at this point. We're aggregating 1800 and 1953 for city 2 and 2912 for city 1. Once we have those results, then this is the late materialization part. Then we translate those 1s and 2s into their final values, which is Perth and Sydney in this case. So one thing to point out here is that in order to resolve this query, and it only has one where clause, one condition, we didn't have to scan anything, right? We were able to use with just that condition. We were able to use one of the dictionaries and its index to find the rows that we needed, and then we very efficiently access the column data from those other columns to produce the result. This is the basic building block in Druid, right? And why it's so fast to process these data files for almost any kind of query. Trying to remember why I bring it back to this. Well, just to remind everyone that so these yellow squares are those files that we're talking about, right? So as we're processing a query, we're going to see that kind of operation that we just went through occur in parallel across multiple historicals and across indexers with the real-time data, and so it's capable of producing results really fast because of the parallelism and because of the efficient mechanism that we use to store and query that data. So, well, any questions there before I start to wrap up? Nope. All right. So I'm going to check the chat. Nothing in the chat. All right. So Druid is I showed you an example of an application built on Druid, and that's the Imply pivot tool, which is similar to Tableau, but you could also use Tableau. You can use Looker, metadata, Metabase, Superset, Grafana. Those can all connect to Druid. Anything that can connect through JDBC or through Druid's REST API in order to process the queries and the results can access Druid. And so we see applications built on traditional BI tools. We see applications built on custom applications built on development platforms like .NET, like Angular, Elixir. Really, again, anything that can do JDBC or can do essentially an HTTP request to Druid can interact with Druid. And you can interact with Druid. Even in the HTTP case, you're interacting with SQL if you want. There's also some native JSON structures to do querying with, but most people gravitate towards SQL because, well, I know I do. It's easier for me to understand than trying to fill in the JSON. And there's data science use cases as well, right? We have use cases where Druid is being used to do analytics on the machine learning models themselves, so on the effectiveness of the machine learning models in real time. We're seeing other cases where Druid is being used to calculate features for real-time evaluation of data models because of its fast analytic capabilities. That's sort of the end of how it works. I have a few more slides to share in terms of use cases. So if you go to the Apache Druid website, so that's druidapache.org, you can look at the Powered By page, and there's all of the practitioners, or many of the practitioners that have implemented Druid tell their stories here, right? And so some of them have links to videos and such that where they describe their use case and how Druid is helping them. There's the Druid Forum. This is a space where the whole Apache Druid community comes together to ask questions and to provide answers. So it's a community-driven Q&A environment. There's space for uploading videos, for uploading blog posts. So there's a lot of information in the Druid Forum, and it's a friendly place for newcomers who are trying Druid for the first time. There's the Druid website itself where you can there's a quick start and there's documentation. You can download the software immediately. The latest release is 0.23, and it's available now. So you can download and go through the quick starts, and it'll guide you through some basic ingestion, some streaming ingestion. It'll show you how to do streaming ingestion, and then how to query the database. There's the GitHub project. This is where we hope to, we're always looking for more committers, not just developers. So not just people who understand the distributed code and the distributed processing and all the Java involved in this, but also people who are just users, right? Who are users of the database and are maybe reporting bugs or reporting or requesting new features of the software. This is where that happens in the GitHub project. There's our company website where we have blogs, both from our engineering team and our company and from the community. We try to interview people from the community and create interesting articles about what people out there in the open source community are doing with Apache Druid. This one's actually one that I like to point out a lot because this is free training, right? We have 2 levels of training at this point, and it's free for now. We're not sure whether it'll stay free, but if you go to learn.imply.io, these 2 courses are available. So the Druid Basics will get you, and these are both hands-on courses. They get you into a virtual environment where you can bring up Druid and they walks you through its configuration, it's data ingestion and querying, and then the more advanced course in ingestion and data modeling that gets into how to really get the most out of Druid. There's also tomorrow, actually, we have our first Druid Summit. That's why I'm here in Seattle. So if any of you happen to be in Seattle, you're welcome to come to the Druid Summit tomorrow. Or there's these other events coming up in Los Angeles, New York, Atlanta, and San Francisco. If you're interested, just go to druidsummit.org and you can register for any of them and see which other ones are available. There's other dates in other cities as well. And finally, I'll leave you with this slide. This is just a ton of ways to communicate with us. I've mentioned a few of them. We also have a Druid Slack channel, so you're welcome to join that. And I've talked about the training program. There's our community email. I'm one of the people who receive that community email, so if you want to talk to me, you can talk to me there. And anyway, these I'll leave these up and open it up for any more questions if you have any more questions. I see some in the chat. Yay, free, yes. There you go.
Yeah, we like the free stuff. Where you can find the recording, Alexander, I'll throw it on YouTube soon. If you're in our Slack group, I'll post it there. Tell you what, I will try to go and put it on the meetup messages or whatever they give me to do that too. But it'll end up on my YouTube channel, Dustin Vanoy, on YouTube before long. Maybe tomorrow, maybe in a week. It just depends. What other questions do we have? Since you're giving us all these ways to dig in more, I think that saves me from my questions. I'll rewatch a couple pieces and see if I can find time to get hands on with the free course. What other questions are out there? See, I didn't lie. Our group got so much quieter since we've been virtual, but give them one last minute to jump in. Anybody? Ike, are you still there? Did you get everything you wanted and more out of the session?
I have a lot of questions, but I'm sure that they're pretty basic, and I didn't want to embarrass myself by asking you. But
There's no such thing.
okay, so I still see a lot of data movement, and right, like the data gets collected and then put in the repository in the caching system, right? So I was concerned about the general data movement, like.
So actually, it's intended to move the data as little as possible, right? In the way it executes the queries, at least. So there is data movement at ingestion time. So there is the process of ingestion does require, you're bringing in the raw data, whether it's streaming or in batch, and producing these segment files, right? But once we produce, so the segment files are produced and put into deep storage, and that keeps them safe. So that's a safe place to put them. That's really what deep storage is about, right? So even if you lose your whole cluster, all the data that you've put in deep storage is still there, and you can bring a whole cluster back just from everything that's in deep storage. So think of deep storage as the backup, right? Just a preemptive backup. You're doing it ahead of time. And then really it's about loading the historicals from that ingested data. Once that's in place, what you really have from a query perspective is the historicals that have the data preloaded locally, and the indexers that are receiving new data, right? And those are the ones that are being queried, and they're really only queried. So they don't talk to each other, right? The historicals don't talk to any other historicals. They're essentially receiving instructions from a broker about what to query, about what to process, and they return results to the broker. So that's really where the most of the actually all of the queries are resolved that way, right? And there's the intention is that there's very little data moving back between the historicals and the brokers, because most queries will, do some kind of aggregation and return a subset of results from each of the historicals to the broker. So anyway, I'm just trying to describe the query side of it. Does that help in terms of the data movement that you're seeing?
It does. I feel like I just need to get my hands on it, probably.
So we're
we
not
always
doing
want-
joins, right?
I'm sorry.
There's no joins, correct?
So joins are limited, right? So there is really no, what I would say, fact-to-fact join, right? At this point, there's actually a new effort starting in the open source project, creating what's called the multi-stage query framework, which will start doing the fact-to-fact joins, but that implies a shuffle, right? That implies shuffling.
Yeah,
data. So
that's
it
kind of
doesn't
what I was calling
imply
out
moving
for
data across units. So right now, all queries are scatter gather. There is a limited join function for lookups, so you can have lookups. And what happens, and these are just key value lists, right? The lookup tables that you can use for, a smallish star schema kind of thing. Where these lookups are cached in memory, and that is the limitation here, right? Lookups are broadcast across all the units of processing that are going to be using them, right? So all of it, if you're going to be using them in joins in historicals, you'll have that same lookup broadcast across all historicals and kept in memory, so that those lookup joins are very quick. But joins in general are not yet there. You can do them, right? It's just not, it's an anti-pattern for Druid at this point, because what'll happen is, if I'm bringing back a lot of rows to if I'm doing two big queries, it'll process them on the historicals, bring back all those results to the broker, and then in a single thread try to do the join. So It's not a good idea, right? That's where the multi-stage query framework is going to change things a bit and enable a shuffle join, which is really what you need in order to achieve that.
Yeah. Well, even that lookup sounds pretty handy.
It's useful. It's useful, yes. Especially if your lookups are changing, right? Because the recommendation is, if the values associated to your lookups don't necessarily change, then it's recommended that you do the joins upstream, right? And it'll just be faster for your queries. Remember, our objective here is to drive interactive applications, right? So doing the least amount of work possible when that query, the application query comes in, is really how you design or how you model these tables.
And then is there a simple way to describe how you handle like updates? Say it comes in with the wrong city and you need to reverse that and have a valid city override it. Is there like a simple way to
lookup
describe
is an answer to that, right? Using a lookup is an answer to that, because you can refresh lookups in memory fairly quickly. But let's say that it's not in a lookup, that it's actually in the data, or that you have a set of transactions. You can do updates. It's not a row update. And remember, these are immutable files of 5 million rows, so you're not going to go change one row. And what you do is actually replace time chunks, right? So you can create another batch and do a full replace of a whole time interval. That's one way. There's also, if we're not talking update, but we're talking append, you can append to time intervals. So you may have created, you batch loaded a bunch of time, and there's just some time interval that is already in place, and you suddenly have a new transaction for that old time interval. You can create new segment files that are part of that time frame, right? And they're just in separate segment files, so you can do appends that way.
Yeah, okay. That gives you a lot of ability to handle it in the application then if you need to, it seems. So.
Yep.
Okay.
Yep.
All right. Any other questions out there? All right, Ike's gonna get hands on, I'm sure, and then in a week we'll be talking about it, and maybe we'll email you or join one of the many
Absolutely.
communities you
You know,
guys
it's
are.
my job. It's my job as a developer advocate to help out and people that are just testing it. So feel free to touch base, you know, to email me, ask me questions. Um, that is sort of my job.
Awesome. Thanks so much, Sergio. We really
All right.
appreciate it.
Thank you.
Thanks to everyone who joined the meeting. We will see you next month. I'll try and get the meeting invite out fairly soon, but it'll be the third Wednesday of the month again. Find us on Slack, follow us on Meetup, and yeah, definitely reach out if you have special requests or any feedback for us. Thanks, everyone, and thanks again, Sergio.
Thank you.